Okay, back up a couple steps. I believe we've already covered this slide, right? I think we talked about moles and what moles were. I'm going to back up a little bit to get going. Keep in mind what we said the mole was. It is a definition. It tells us how much of something is there. It's sort of like the dozen. Dozen means 12. A mole means this many right here. Okay, 6.022 times 10 to the 23rd. Get to know that number. Become familiar with that number. It'll be your friend. Now, first of all, it's called Avogadro's number, named after the scientist who sort of figured this out. But it becomes a very powerful tool for you in that it allows us to count the number of atoms present in a more efficient manner. You can see that that's a really big number, so by lumping them, that many of them together, and once we have that many, we can say we have one mole, and that's easier to count. Okay, that's the reason that we're doing this. But also, one of the things that I mentioned is that the way that sort of Avogadro determined all of this, we said that 1 mole of carbon atoms weighs 12 grams. Okay? Through what he figured out and through what I've said in lecture here, what we can now assume is if you look at the periodic table, 2 things about the numbers that you see. The whole number that you see, like hydrogen's, the whole number with it is 1 above the hydrogen, or up to the left, depending on your table, whatever. That whole number, of course, is the atomic number, and it tells us how many protons are there and defines the element. You'll also see the atomic mass of that particular atom underneath it in decimal form. That means that's how many AMU it weighs on average. How many protons and neutrons, that's the sum of the protons and neutrons that are in that atom. And they're decimals, of course, because we said different isotopes exist for different elements. Now, what that number also means, it has a double meaning. Number 1, it means AMU of 1 atom, but also it tells you something very, very important. It tells you how much 1 mole of that element would weigh in grams. Okay, that's what that number is. For example, hydrogen is 1.01. That means that if you had this many hydrogen atoms, and you could collect them and put them on a balance and weigh it, it would weigh exactly 1.01 grams. So you've got a different unit now. Instead of AMU, we can use also the unit gram, but it applies differently. Okay? So that's going to become very important. All right. I think I did this example already, right? Well, let's review to make sure we can follow. I say a silver ring contains this many silver atoms. How many moles of silver are in the ring? So basically what I'm asking you to do in this question is, if I know there's this many atoms present, how many moles would that be equal to? And what you need to know is Avogadro's number in order to answer that. It's sort of like me saying, I have 3,217 donuts. How many dozen donuts do I have? It's the same type of question. Okay? I want you to regroup it into a different unit. All right, so the way that you would do this, figure out what you know. Obviously, that's the only thing given in your problems. You know that you're going to moles, and you know this to be true. Now, this can be your conversion factor. I had you set up the math from the previous chapters in a certain way because when we start getting into more things like this, you're going to need that mode of operation. You're going to need this times something over something else to create these conversion factors. Here's what we do know. If we have 1 mole of silver atoms, if we had that, that's how many silver atoms we would have. So these 2 things become equal and thus become a conversion factor for us. Okay, so we know we're going from atoms of silver to moles of silver. How can we get there? We use this conversion factor. We know that if we're starting with atoms, if we put some kind of relationship here, we want to get to moles, we want to leave atoms of silver. If we put atoms silver down here and figure out a way to put moles up here, that's what we're going to get to. These are going to cancel out. You're going to be left with this, and that's how we get our answer. Okay? What you'll see is when you're solving problems like this in general, like back when you did generic conversions of units and that kind of thing, there's a lot of different ways to get to the same answer. You can go through different paths. All that matters is if you keep track of your units and cancel stuff out, whatever's left, that's a fair way to get it. If the only thing, whether I do this in other steps or whatever's left, if moles are left after I've canceled everything out, I can be sure that the number of I've calculated the number of moles, and my answer is probably right, so long as I did the math correctly. I can type things into my calculator and hit equals. All right, so let's put in real numbers here. We know that we have this many atoms of silver, so we would rewrite what we see here in actual math and do the math. Take that times that, which would be that, right? Then divide it by this, and I'll get an answer in moles. Cross out the things that cancel, and I get 1.8266 times 10 to the minus 2 moles of silver. Keeping in mind I'm limited to 2 significant digits over here, right? As such, my answer is 1.8 times 10 to the minus 2. In other words, 0.018, right? Right? 0.018 is the answer. Now, 0.018 is a smaller number, much easier to deal with than this large number here. If you had to write that all out and keep track of the math there. That's why we use moles. It's an easier way to group up this stuff and keep track of it. Okay? All right. Then you can check it to see if it makes sense. And we already did that last time we did this. Okay. I mentioned this already a little bit, but relationship between moles and mass. When we have 1 mole of an element, like anything that you see on the periodic table, if we have 1 mole of it, however much 1 mole of it weighs, that's what we call its molar mass. Okay, so how much does 1 mole of it weigh? That's its molar mass. And what's nice is, like I said, this is already found on your table. It's actually, the molar mass of an element is going to be expressed in grams, the molar mass. Because if you have a mole of it, you've got a whole lot, enough probably you can actually measure it on a scale. So we can use grams instead of AMU. So the molar mass is going to be in grams, but it's going to be numerically equivalent to the AMU value that's listed on the periodic table. So make sure you understand that. But take a look at how certain things compare. This is important that you can grasp. Take hydrogen, for example. Notice that here's a bunch of different things that are found on the periodic table, different elements that are present. 1 mole of each of them is the same value. It's this many atoms. 1 mole of hydrogen is that many hydrogen atoms. 1 mole of sulfur is that many sulfur atoms. That doesn't change. It's the same. What is different, though, as you can imagine, as the bigger the atom, if you have hydrogen, which is very small, it's only 1 proton big. If you have sulfur, what is it? 32 is its mass, right? So it's got 16 protons. Sulfur is a much bigger atom than hydrogen. It's got 16 protons, 17 neutrons, or 16 protons, 16 neutrons in general, usually, in its most stable form. Hydrogen has 1 proton, that's it. Big difference in terms of how much they're going to weigh, right? So that it would make sense then, if you had a mole of sulfur and a mole of hydrogen, which one's going to weigh more? A mole of sulfur. It's like, which one's going to weigh more, a mole of ping pong balls or a mole of elephants? It's not hard to figure out that, okay? So what you'll see here is the weight of 1 mole of hydrogen is this, and you can see that the weight of this many atoms, or 1 mole of all these things, are listed here in increasing order because these atoms actually get bigger the way I have them listed as you go down. Okay, so keep that in mind. Take a look here. Here's some visualization so you can see. You remember when you checked into the lab, you had a watch glass. It was, it should have had a watch glass, I think. It was sort of like, it looked like a lens, sort of, and that's what you see here. And notice how much sulfur you would see on this watch glass. That's powdered sulfur. That's actually how much it would take to get a mole of sulfur, about 32 grams if you weighed it on a scale. I don't know if you weighed anything, I can't remember. Yeah, you weighed out the metals and stuff for the specific heat lab, so you get an idea of, you weighed like, how much, 50 grams? Right, so this would be less than that. You can imagine in your head sort of how much I'm talking about here in terms of weight, because you actually held that. So 32 grams is what you'd have to get actually that many number of atoms of sulfur. Whereas if you have carbon, pure carbon, sort of looks like coal. In this case, it's probably what it is. If you had notice this is a smaller sample. But that makes sense because the carbon atoms are smaller than the sulfur atoms. So they can occupy less space. That's why it's a smaller sample. But there's still just as many in number in that sample as there is that sample. So when you weigh that many carbons, a mole of carbon, it only weighs 12.01 grams. Okay? So hopefully that makes sense. So now we can actually convert between grams and moles of samples of certain elements or compounds or what have you. This is going to become very, very important to you because in the very near future, you're going to be working with moles extensively in chemical reactions. This is how you're going to keep track, because you've got to know how many of these things are reacting with how many of these things, how many of them like to react with each other, and how many things are going to be produced as a result. But the problem is you can't count atoms. We don't have any lenses we can sit in the lab and try to count these atoms. So guess how you're going to have to count your atoms? By mass. You're going to have to weigh out your samples. You're going to have to figure out how much mass you have, and then use this conversions like this to figure out how many actual moles of atoms are present so that you can keep track of how many of things are reacting. So this is going to become very useful. You've got to know how to do this. Okay, you've got to. You've got to be able to convert between grams and moles of atoms. Okay, that being said, do this. Calculate the number of moles of sulfur in 57.8 grams of sulfur. What do we need to know in order to answer this question? How much what weighs? Yeah, we need to know how much 1 mole of sulfur would weigh. That's our conversion factor. Okay? Now, we have 57.8 grams. Basically, we want to see how many moles that is. 1 mole is how many grams according to the periodic table? 30. Okay, so 32, that or thereabout. Okay, so if we know that we need 32 grams to equal 1 mole of sulfur, we're going to have more than a mole of sulfur here, right? That makes sense because we have 57.8 grams. Now, your task is to figure out how many moles do you have. How many actual sulfur atoms are in that amount? And this is why you need this conversion factor, this Avogadro stuff. Okay, so keep in mind what you're doing in your head and then set it up accordingly. We know this. You just told me this. It's off the periodic table. 1 mole of sulfur atoms would weigh that many grams. Okay? You're going to go from grams of sulfur to moles of sulfur. How will you do that? By that, what you just said. You know this to be true. That's your conversion factor. It links you from one place to the next. So set it up. Take 57.8 grams of sulfur times 1 over 32.06. Now, in your head, you could have just said, okay, well, if I know that for every 32.06 grams that are there, I've got 58, divide it in my head. Yeah, that's the way you go about it in everyday life. But do it this way, okay, for now, so that you don't get stuck down the road. Set it up like I have it. Use conversion factors, okay? You know that for every 1 mole of sulfur, if you had 1 mole, it would weigh 32 grams. You have 57.8 grams. Set it up like this. Do the math. You would find that after canceling out, there's your raw number. Keep in mind you've got 3 digits here, 4 digits there, so your answer will have 3 digits. 1.80 moles of sulfur. That makes sense, right? Because you told me that 32 grams makes up 1 mole of sulfur, and you have more than 32 grams, so your answer should be more than 1 mole. Okay, that makes logical sense. All right. If you would have had 64 grams, you could safely have guessed that you would have how many moles? You would have had 2 moles. You know that it's less than 64, right? You have 57.8. It's less than 64. It's more than 32, so you know that it's somewhere between 1 and 2 moles, and that is verified by the answer that you got. All right. Any questions about that before I move on? You know everything. We'll see. Okay. Now, let's put it all together. You should now be able to convert between 3 different things in terms of what we're doing in this chapter. You should be able to go from grams of something, a mass of something, turn that into how many moles you have. Okay? You should likewise be able to go in reverse. If I give you a mole value, be able to convert that into a gram value. What do you use? Begins with a M and ends with a molar mass. Molar mass. Okay? You will use the molar mass to go from either one of these directions. Just a matter of how you want to flip the numbers in your conversion factor. You can go either way. How would you go from moles to atoms or atoms to moles? What do you use? Huh? I heard it. Avogadro's number, right? That's a definition of what a mole is. If you want to know how many atoms and you want to go to moles, you got to know how many atoms are in a mole. If you want to go to moles to atoms, you got to know how many atoms are in a mole. That's Avogadro's number. Okay? So you can go. Now, the point of this is because if I give you a gram, for example, if I say you have 32 grams of sulfur, how many atoms of sulfur are present? Realize that before you can ever calculate the number of atoms present, you first have to calculate the number of moles that are present. Okay? Because that's the only thing that molar mass allows you to calculate is the number of moles. So my point here is you'll see that moles is actually in the center. You cannot go straight from grams to atoms or atoms to grams without going through moles first. Okay? Moles is sort of the central hub of all of this. It's extremely important. So from here, you can go back and forth. From here to here, you can go back and forth. But to go from either end to either end, you got to go through moles to make that happen. So keep that in mind. So take your aluminum can. It's pure aluminum. Put it on a balance. Say it weighs 16.2 grams. You can actually calculate and impress whoever you want how many actual aluminum atoms are in this can. Okay? How many aluminum atoms are in an aluminum can with a mass of 16.2 grams? Walk me through it. Don't look on your paper. Before we do any math, tell me my logic. What am I going to have to first do? That's right. I'm going to have to find how many moles of aluminum is represented by 16.2 grams. How do I do that? What do I use? Molar mass. Exactly. Once I answer that, I've got moles of aluminum. How do I turn moles of aluminum into how many atoms of aluminum are present? That guy's number. That's right. Avogadro. Amadeus Avogadro. Okay. Anybody ever look him up like I told you to? Look up a nice picture of him? You need to do that. Oh, I see. I see. Yeah, you should have big banners of him and have a big mole day party. You're right. Most definitely. You know, anybody will look for a reason to party, right? So there you go. Mole day. It's just another day to put on your calendar. All right. So you know this to be true. You just told me that. Okay. 1 mole is equal to this many. We've already discussed this. This is Avogadro's number. And you can also find how much 1 mole of aluminum atoms would weigh based upon your periodic table. Look it up. Find the number. You'll see that it's about 26.98. Okay. Depending on what table you're using, it may be rounded differently. But pick whatever number of the table you're using. Okay. Now, we're starting at grams. You know that you have 16.2 grams. You said we have to go to moles. So let's go to moles. After that, we're going to go to atoms. Now, let's fill in how we get from one step to the next. To get from grams to moles, like you say, molar mass. Okay, set it up just like that so things can cancel out. That leaves us with an answer in moles, but we're not done because we need to get to atoms. So let's string another one next to it. Say this to be true. We know that this many atoms, or this many of anything, we're dealing with atoms here. It could be anything. You know, it could be molecules, whatever we decide to define it as. In this case, we're talking about atoms. This many atoms of aluminum are in 1 mole of aluminum. So notice that when everything cancels out, you're going to be left with an answer in atoms of aluminum, which is what we want. So let's put in real numbers now. Here's what our 16.2 that we started with times our first conversion factor. Use the molar mass to get to moles. Now we can use Avogadro's number to go from moles to actual atoms. Cancel everything out, you get that number. Okay, we got to incorporate significant digits here. We're limited to 3 over here. That's going to limit our calculation. So our final answer, 3.62 times 10 to the 23rd atoms. So a lot of atoms there. Questions about this? Do you follow me? Even if you can't do it on your own right now, do you follow the reasoning that I'm doing here? You'll take practice. You'll have to do it yourself, but you can certainly figure it out. Okay. Now, does this make sense? Ask yourself. Assuming that you got this answer and you understood how to get to this point, does an answer of 16.2 grams make sense? Well, let's consider. If you had 1 mole of aluminum, how much would it weigh? Okay, almost 27 grams, right? Okay, so that means if you had 27 grams, let's say, of aluminum, how many aluminum atoms would be present? 1? how many atoms would be present? That's right. If I had 27 grams of aluminum, I would have 6.022 times 10 to the 23rd aluminum atoms present. Since I have less than 27 grams of aluminum, which is what 1 mole would be, it makes sense that I have less than 6.022 times 10 to the 23rd atoms of aluminum present. So at least, even though we can't check the numbers exactly without going back and checking the math, we can at least see that it makes sense. Okay? All right. Ask me if you have questions, otherwise I'll keep on going. Nothing? Very well. All right. Now, let's take it a step farther and do the same thing we have been doing, but let's make it compounds, because in real life we know that elements don't really exist all that commonly in nature. Typically the elements that you see on the table are not in pure form. Typically they're tied up in compounds and other chemical bonds that exist in the universe. So we got to apply that to what we would actually see now. We can actually find the molar mass of any compound. Guess how do you think we do that? Yep. You look up each individual atom that you have in your compound. Add them up. Add up their weights. If you have NaCl, how much would 1 mole of NaCl weigh? Well, if you had 1 mole of NaCl, how many NAs would be there? 1 mole, right? And if you had 1 mole of NaCl, how many Cl's would be there? 1 mole. So add up the molar mass of Cl, and add to that the molar mass of sodium. Put them together, you got the molar mass of sodium chloride. It's that simple. Just add. All right. Excuse me. Notice that if I just wanted you to take the formula mass, how much does one water molecule weigh? You would just do it in AMU, right? You would, realize there are 2 hydrogens and 1 oxygen. Each hydrogen's about 1. Each oxygen is 16. You've only got 1 of those. So add it all together and you get about 18.02 AMU. Well, if you know that you have 1 mole of water, now imagine this in your head. You've got 1 mole of water molecule. So you've got all these water molecules, 6.022 times 10 to the 23rd of them. If you have 1 mole of water molecules, and you had it, and you were looking at it, and I said, okay, count. Tell me how many oxygens you see. How many would you see? 1 what? You would see 1 mole. Now imagine this. Let me simplify it down. What if we had 2 water molecules? Only 2 molecules. Here's 1, here's 1. I have 2. How many oxygens are here? 2. How many hydrogens are here? 4, right? I have 2 waters, but I have with that 4 hydrogens. So if I actually had to count the hydrogens, I'd have twice as much as what I had of water molecules. Now realize that you can do the same thing with a mole, right? You just multiply it by 6.022 times to the 23rd. So whether or not I have 1 or 1 mole, I can keep track of it the same way. If I have 1 mole of water over here, and I have 1 mole of water molecules over here, how many moles of oxygen do I have? Good, 2 moles. How many moles of hydrogen do I have? 4 moles, okay? So what I'm saying here is since 1 mole of water contains 2 moles of hydrogen and 1 mole, if I just had 1 mole, I did it with 2 moles there, but if I just had 1, you would have 2 moles of hydrogen, 1 mole of oxygen, right? So that means you can add up the molar masses of each one of those. You can look up hydrogen, how much 1 mole of it would weigh, how much 1 mole of oxygen would weigh, put it together, and you've got how much 1 mole of water would weigh. All right. So there you go. You'll notice it's the same thing as up here, except we're using grams instead of AMU. Oh, okay, so that says converting between grams and moles of a compound now. Same as before. To go from grams to moles, we need to use what? Molar mass. To get molar mass of a compound, we've got to add things together. That's the only difference with this problem than what we've done before. All right, so take a look. Calculate the mass in grams of 1.75 moles of water. Yeah, that's an abbreviation for mole. You drop the E and save yourself a ton of time. 1.75 mole of water. How do I turn that into grams? Well, like you say, I need to know the molar mass. I need to know how much 1 mole of it would weigh. And I can get all that information from the periodic table. So I'm going from moles to grams is where I'm going here. Okay? So here's what I'm going to need to know. Excuse me. What I'm going to need to know is this right here. Where did this come from? This comes from adding up these guys right here. 1 mole of water would be whatever 2 moles of hydrogen would weigh and 1 mole of oxygen would weigh. So 16, 17, 18. Each one of these is 1, right? So I add that up. It's about 18.02 grams for every 1 mole of water. Make sure you understand where I get this number from. Yes or no? If you don't, tell me. It comes from the periodic table. I just add up how much each one of those things would weigh. Okay? All right, I'm going to need that. I'm going from moles of water to grams of water. So I'm going to use that which I just figured up by adding up on the periodic table. So I take 1.75 moles of water times whatever the molar mass is. That's this ratio here. I've got 18. I know that if I have 18 grams of it, I have 1 mole. Okay? So then these are going to cancel out. I'm going to be able to convert my moles into grams. Much more useful in the lab because we can't measure moles. There's no instrument that measures moles. Think about it. It makes sense because it would require an instrument that goes in and counts all the atoms. That's ridiculous. What you can do is measure mass and convert between mass and moles. That's what's going to be very useful. Do what? That's right. That's exactly right. Now we can just weigh it and use his math to convert that into an actual number. That's exactly right. Okay, so we're limited here to 3 sig figs because of our 1.75, so 31.5 grams of water. Okay. You can check it to see if it makes sense by the same methods that we have been before. Converting between grams and number of molecules. What's the key? What do I have to go to first if I'm starting with grams? Got to go to moles. Then I can use what to go from moles to... Do I go to use molar mass to go to number of molecules? Avogadro's number. Okay? It's the same as before. Here's the question. If I had 4.78 times 10 to the 24 molecules of nitrogen. How would I say that? You know how to name things now. How would I name this? How do you name 2 nonmetals? Technically, they're stuck together. Uh-oh. Okay, we're going to use prefixes. Now, you see NO2. NO2 negative could be nitrite, but it's not an ion. You don't see a negative sign up here. You only call it nitrite whenever it's an ion, okay, when it has a charge. Here, this is actually NO2, charged neutral. It's not an ion. It's an actual compound. How do I name it? Nitrogen dioxide. We use prefixes when we have 2 nonmetals. It's a molecular compound, right? It's not ionic. It doesn't involve any metals, so we don't use any of the other things that we've talked about, like the metal and then the "ide," and then maybe if it's a type 2, put the Roman numeral in the middle. Doesn't apply. It's very, very easy to name non-metal compounds like this. You just use your prefixes. Okay? Not mononitrogen either. Remember, we dropped that if that's there. So it's just nitrogen dioxide. All right. Find the mass. If we have nitrogen dioxide and we have that many molecules of it, how much would it weigh? So we got to start with what we know. We've got this. How are we to go from molecules to grams? We've got to go to moles first. So we got to use our the number of molecules to get to the number of moles. What do I use? Avogadro's number, which is defined down here. Okay, 6.022 tenths in the 23rd. Now, once I get to moles, see, this is what's going to. This is why chemistry is a little bit harder than just regular old math. What we got here is we've got to make a map in our head where we're starting, where we're going. You have to have an idea. If you just start randomly plugging in numbers to things and try to memorize steps, you're going to get lost. What you've got to realize is what we just reasoned through. Okay, I'm starting with molecules. I've got to get to grams. How do I do that? I've got to go through moles. To get from molecules to moles, I've got to know Avogadro's number. Once I do that, I'm at moles. To get from moles to mass, I've got to use the molar mass. Okay, you've got to make this map. You've got to be able to find and navigate your way from point A to point B. Otherwise, you're going to get lost with all the math in the middle. Okay? Especially when it adds more steps down the road with more complicated math procedures. Okay? All right. So what we know is this. We know that 1 mole is defined as this. And we also know that since we're going to have to use the molar mass at some point down the line, we have to calculate it. So if we had 1 mole of NO2, how much would it weigh in grams? If we had 1 mole. Well, you look up how much 1 nitrogen would be, which is what, around 14 grams. Oxygen is 16, right? So 32 plus 14, you got 46 grams, that or thereabout, 46.01 grams of nitrogen dioxide. That's how much 1 mole would weigh. So with these two things, we can answer our question. All right. So I'm going from molecules to moles to grams. Here's my equation, or the conversion factors that I'm going to need. To go from molecules to moles, I need Avogadro's number. How many molecules are in a mole? Once I know that, I'm at moles, I need to go from moles to grams. Okay? I need the molar mass. I need to know how much 1 mole of it would weigh, if that was the case. Then I can plug in real numbers, cancel out accordingly, and I would get this answer. So I'd multiply everything on top. This is a safe way to do it. If you're good at math, you don't need to do this. You know how to do it properly. But if you're not, realize the safest way to do this is multiply that, times that, put a number over here. Then multiply everything on bottom, put a number, then do one final step where you take the top divided by the bottom. That way you don't get your numbers all confused. Okay? When you do that, here's your answer. But we've got 3 sig figs over here. That's going to limit us. Okay? So 365 grams of nitrogen dioxide. If you had this many molecules, okay, it would weigh, I guess, that much, 365 grams. So it would weigh a considerable amount. Okay, almost a little less than a pound, right? How many grams are in a pound? I know? See, we're in the United States, we don't use a metric system or anything like this, so we never have to know this crap. The rest of the world does. 454 grams per pound. Okay. Do I need to review any of that? Judging by the complete absent looks on your faces, not sure how to interpret. I'm going to assume that means I have no idea, but if you review, it won't help me anyway. So that's how I'm going to interpret that. Yeah. The box that you showed us. Oh, yeah. I guess I'm assuming that you know how to operate your calculator, but maybe that was an unsafe assumption. Make sure that when you type in Avogadro's number into your calculator, okay, you type in 6.022, then what do you type? Okay, EE or EXP, depending on your calculator, okay? Then you would type in, after that button, 23. Don't type in 6.022. Hit the multiplication sign, hit 10, try to raise it to the exponent of 23. That'll work probably most of the time, but there's a reason I want you to not do that down the road. Okay? Use 6.022, hit EE or EXP, whatever button your calculator operates on. And then after that, you just enter the exponent value that you want. Okay? And that's how you would enter that. Or EXP. What's the brand of your calculator? It's right here, the big EXP button in the middle. All right, I'm just teasing. Fine. All right. Now this is a little elementary, but bear with me. Okay? We know certain things can be equivalent to something without actually being sort of equal to something. You'll see what I mean. For example, you can't really have a chair, a useful chair anyways, without having 4 legs. Now, I'm sure you could get some kind of tripod type chair, but don't overanalyze the situation. Okay? Stay with me here. So a chair by definition is a chair if it has 4 legs, we'll say. For a spider is technically supposed to have 8 legs. Okay? So we can say that 8 legs is equivalent to 1 spider. We could say that 4 legs is equivalent to 1 chair. Likewise, if we looked at it from a chemical perspective, if you had a water molecule, this is oxygen, hydrogen, hydrogen, we would say that 2 hydrogen atoms are equivalent to 1 2 hydrogen atoms are equivalent to 1 water molecule. You've got to have this to get this. That's what we're saying here. Notice I didn't say equal. Okay, I used a different sign because technically you can't argue that they are equal, but you can say they have a relationship of equivalency between the two. Now, as such, we can use these as conversion factors. Okay? Good old conversion factors. Never going away, ever. Okay? So, you know, if I said I had 24 spiders, how many legs were there? Okay, I know that in your head you could say 24 times 8. But if you had to set it up in terms of a conversion factor, you would say 24 times, 24 spiders times 8 legs over 1 spider, right? Okay, so that's the way you set up these conversion factors. Now with spiders and things that you're used to, that may be easy to do. When I start throwing in chemical formulas, you go crazy and can't think in the same way anymore. So it's best that we set up things in a very systemized approach. Okay, a systematic approach, I guess, would be the better word. All right. Also, likewise, with this water molecule, I could say, okay, 2 hydrogen atoms are equivalent to, or 2 hydrogen atoms are present for every 1 water molecule. I could also say 1 oxygen atom is equivalent to 1 water molecule. Okay, either way, it works. It's just an expression to explain what I see there and how they're related. Okay, now, if we know, this is where it gets kind of tricky. If we know how much of a compound we have, sodium chloride, for example, if I tell you to weigh out a certain amount of sodium chloride, okay, and you can then easily convert, if it's pure sodium chloride, which is table salt, you could eat, well, non-iodized table salt, but some iodized table salt because it's sodium iodide mixed in with sodium chloride. So you know that. If you had pure sodium chloride and you weighed it on a balance, you could take that mass and convert it to moles very easily, and you could actually come up with a number of sodium chloride molecules that you have there. Now, what if I asked instead, okay, how much sodium is there? I don't want to know how much sodium chloride is there. I want to know how much sodium is there. Or I could equivalently ask how much chloride is there. That's a little tougher to do because that's not what you measured. What you measured was the entire formula, like 1 unit of sodium chloride, how much that weighed. And what you got to keep in mind also is that, you know, sodium and chloride are different sizes, right? Sodium is actually smaller than what chlorine is. So as such, they're going to weigh differently. So you can't just say, oh, it's going to be half of whatever I weighed. If they weighed exactly the same, you're right. It would be, you know, you would have as much sodium. If sodium and chloride weighed exactly the same and you took a mass of it, you divide it exactly in half, that's how much of each you have. But that's not the way the elements work, right? Everything weighs differently. So how do you do this? How do you come up with these answers? We can answer this because here's what we do know, keeping in mind what I just said about equivalencies. Okay? Take 1 mole of sodium chloride, for example. What does that mean? That means if I have 1 mole of it and I pulled it apart into its pieces, how many sodiums would be present in 1 mole of sodium chloride? 1. It's sort of like how many sodiums would be present in 1 molecule of sodium chloride? 1, right? If I had the same question in reference to chloride, how many chlorine atoms would you see in 1 mole of sodium chloride? 1. Okay? So I could say this as 1 mole of sodium is equivalent to 1 mole of sodium chloride. I could say that 1 mole of chlorine is equivalent to 1 mole of sodium chloride. You see what I'm saying? See where I get these from? Okay? Based upon this. Let's look at water. What if I bust up water and pull apart its constituents? If I take 1 mole of water, how many mole of oxygen would be in 1 mole of water? 1 mole. How many moles of hydrogen? 2 moles. So 2 moles of hydrogen is equivalent to 1 mole of water. 1 mole of oxygen is equivalent to 1 mole of water. Okay, what about something down here? More numbers now. 1 mole of, what is this? Good, calcium carbonate. Okay, Not calcium something carbonate, because it's not a transition metal. It's an alkaline earth metal. Calcium carbonate, chalk, limestone. That's what calcium carbonate is. If I have 1 mole of calcium carbonate, notice, I would have 1 mole of calcium present. I would have 1 mole of carbon present. Since I have 3 of these guys, oxygens attached into 1 molecule, if I separated them all out, I would have 3 moles of oxygen present, right? So I would say, one of the equivalencies I could say here is that 3 mole of oxygen is equivalent to 1 mole of calcium carbonate. That makes sense. Glucose would be the same way. 6 moles of carbon, 12 moles of hydrogen, 6 moles of oxygen in 1 mole of the entire compound. Okay, now that being said, this problem says converting between grams of a compound and grams of a constituent element. If I know what I'm weighing and I know how much the compound weighs, how can I possibly go about figuring out how much of a mass of a certain element I have within that compound? Okay? I use what I know, everything I know so far, plus what we just talked about. Okay, so put it all together. Exciting, I know. It's just enthralling stuff. Carvone, which is the spearminty oil, the smell that you would get off that. Okay, carvone, C10H14O. It's a relatively large molecule, right? A lot of atoms in there. That's actually very small, even for an organic molecule. Your biological molecules are much bigger than that, like vitamins and stuff like that. It has a pleasant odor and a mint flavor. It is often added to chewing gum, liquor, soaps, and perfumes. That's the flavoring agent that we're talking about here. If I had 55.4 grams of that compound, okay, I have this and I know it, I want to know how many grams of carbon. The mass means grams, right? Find the mass of carbon alone. Basically, how much of this 55.4 grams of the entire molecule, how much of it is just due to carbon alone? Okay? Now, to you, this may not seem important, but realize that this is very important in the real world, because the way that we get the elements that we need, especially like gold and silver and that kind of stuff, but anything, really, realize that these things exist in a form that is already bonded to something else. It's not like you go digging and all of a sudden, you know, you're digging for copper, you're digging for nickel, you're digging for gold and silver, and all of a sudden you have this pure lump of silver underneath the ground somewhere. Doesn't happen. It's usually some sort of ore. You've heard of like ores before. It's a combination of other things mixed in with it. You have to figure out how to get it out of there. Okay? We'll do some experiments, and similarly, I'll show you how to take a liquid solution, for example, of copper, and how do you get the solid copper? How do you get it to precipitate and pull out and get pure copper out of a solution of copper? It's relatively easy to do. So in this case, like in those cases, if you're how much ore do you have to mine to get a certain amount of this stuff? If you want to extract it, you got to make it worth your while, especially in an industrial type of setting. People got to make money off of all this. So keeping track of, if you want a certain element, how much of this, the ore or whatever, do you have to use to extract out this element to get a certain mass of it? Okay, so here you got 55.4 grams of carvone. I want to know how much carbon, how much mass of carbon is in that. Okay, now let's reason this through before I show all the steps. If I know how much carvone I have in terms of grams, what is probably the first logical step that I want to take and find out what? That's right. I'm going to want to find out how many moles of carvone I can get, or how many moles of carvone is represented by my mass. How do I do that? What do I use? I use the molar mass. How do I calculate the molar mass of carvone? Add them all together. I look up whatever it was, C10H what? I forget. H14O. I look all that up, and I add it together, and I have the molar mass. Okay, so here's what I can do. Equipped with this information, I can take my gram value of carvone, turn it into a mole value, right? If I know how many moles of carvone I have, using equivalencies, what can I calculate, do you think? Bingo. I can figure out how many moles of carbon would be present if I know how many moles of carvone that I have. Because I know there's 10 carbons for every carvone, right? For every 1 mole of carvone I have, I'd have 10 moles of carbon. Okay, that means I can get to an answer where I can get moles of carbon. Oh, now we're on the downhill, right? Because once I know how many moles of carbon I have, what can I do? Change it to grams. Using what? I'm going from moles to grams. How do I go from moles to grams? Molar mass of what this time? Carbon. Okay? You see the reasoning process. You've got to be able to see this through. You can't just start writing crap down and hope you get to the right place. You've got to think about what you're doing. Okay, I'm going to go through it one more time, then I'm going to show you the problem. Here we go. I've got 50, however many grams of carvone. What I can do with that 50 whatever grams is convert it to moles. If I use the molar mass, I add up everything, and I convert it to moles. If I convert it to moles, I have moles of carvone. Now I have power because I know the formula for carvone, right? The formula for carvone is C10H14O. That means for every 1 mole of carvone that I have 10 moles of carbon present. I use that as a conversion factor. I go from moles of carvone now to moles of carbon. Now I've got moles of carbon. I can easily go from moles of carbon to grams of carbon because I know the molar mass of carbon. Okay? That's the sequence of events. Now what you're going to see in a later chapter, just not to scare you but to pump you up, okay? What you're going to see in a later chapter is, that's assuming that you know the chemical formula. What happens if you don't? What if you have some compound and you don't know what it is, but I ask you all of these questions? Then I'm going to teach you how to deduce the chemical formula from data that you're given. Okay? How to use the fancy machines they use on CSI, like the GC mass specs, and how to determine what unknown chemical is present. Okay? And then answer all these questions. It gets kind of exciting when we do that. So, well, wait. We've got to save it for the last, so you go out on a high. All right. All right, so what we just said, we went through our reasoning. Here's some information that we're going to need to know. Now, if you could mentally map all of this before you start, you'll know what you need. You'll figure out what you need to figure out, what you need to know, that kind of thing. Okay? You could certainly come up with this as you need it, as you're going through the problem, but I'm going to go ahead and list it up here as things that you're going to need to know to solve this problem. We know that we are going from grams of carvone to moles of carvone. So what we're going to need is the molar mass of that, and that's this. 150.2. Where did that come from? I had to add it all up based upon the formula that I have. I've got 10 carbons, 14 H's, 1 oxygen. Add it all up, I get 150.2. Okay? So there's my molar mass. I'm going to need that. I'm also going to need to know this equivalency. For every mole of carvone that I have, I've got 10 moles of carbon. Okay? I'm going to need to know that. And I'm also going to need to know, to get from moles of carbon to grams of carbon, I'm going to need to know that 1 mole of carbon weighs that much. It weighs 12 grams. All right. There's everything I need to know. So we're going from grams of carvone to moles of carvone. Moles of carvone to moles of carbon. Moles of carbon to grams of carbon. Okay? Bam, 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 bam. We're going to have 3 steps, 3 math steps involved here. We're going to start stringing some stuff together now. All right. Told you, don't fall behind. Don't think you can skip a chapter, my friends, because it ain't going to happen. All right, going from grams of carvone to moles of carvone. I need the molar mass. There it is. Okay? Grams to moles. Now I'm at moles. I'm at moles of carvone. I got to get to moles of carbon, because the question was how many grams of carbon are in the mass of carvone that I had. So in order to get to grams, I've got to get to moles first. Okay, so there's my equivalency that I know to be true. That will give me an answer in moles of carbon. Now, once I have moles of carbon, I can get to grams of carbon using the molar mass of carbon. So if I put in real numbers, looks good, doesn't it? A lot of numbers up there. Cross out everything that cancels. I'm left with grams of carbon. Here's my answer. Sig figs, looks like I've got 3 over here. This, don't worry about sig figs on this, right? Because that's a definition. That's not a measured value. That's just by definition, that 10's a perfect number, that 1's a perfect number. So that won't impact your sig fig. So 4 there, 4 there, 3 there, so I'm going to have 44.3. That's my answer. So notice that out of the 55.4 grams of carvone, look how much of it was made just from carbon, 44.3. This is especially important, like for people who are monitoring Sodium intake, dietary types of science, chemical food sciences. People are in this kind of field that develop these diets and these regimens for, feeding regimens for hospitals, health centers, that kind of stuff. Someone has to come up with this stuff. So what you've got to realize is if you're going to eat salt, how much sodium are you putting in the body? Not just how much sodium chloride, because the chloride may not be as important. Maybe you're worried more about the sodium or other things in a similar nature. So you've got to be able to isolate this out. Now the bulk of it is certainly carbon, because carbon is going to be the heaviest. Well, no, it's not actually the heaviest. Oxygen is the heaviest element present, but you've got only one oxygen and 10 carbons. So it makes up the bulk of the mass of this particular molecule. All righty. Oh, good. I was hoping we'd get here. Percent composition. Okay? I know. I got a little saying, right? Everybody looks up at the clock. Attention clock watchers, time will pass, will you? That's the question. Okay? So let's focus up here. Percent composition. What this will be in a measurement of is in a similar fashion. We're talking about, if we have a sample of carvone, how much grams of it is going to be of carbon. What if I wanted you to break it down and give me an actual percentage distribution of all the atoms present in there? Okay, like for example, for carvone, what percent of carvone by mass does carbon make up? How much percentage of carbon does oxygen make up? How much percentage does hydrogen make up? We call this the percent composition of the elements in that compound. Here's how we do it. Okay? No, you say no. I say yes. We're dealing by mass, so everything is going to be determined by the mass of the things that were involved here. That's what we're going to use to calculate our percentages. We're going to need to know the formula of the compound, which is easy. We're going to need to know the experimental mass of the compound. In other words, how much of it you have. That'll be given in the lab that we do associated with this. You'll have to sort of come up with your own and that kind of thing. You'll weigh out a certain amount or whatever, but it'll be known. Okay. The percentages may not always total 100% exactly. Realize that 100% is everything, right? So if you have a percentage of carbon and a percentage of hydrogen and a percentage of oxygen for carvone, when you add up the percentage of each, it should equal 100%. Well, that's in a perfect world. Realize that whenever you actually run this, and whenever you do a similar lab in the laboratory, chances are you're going to lose some stuff. You're not going to measure things exactly right. So when you add them up, you're going to get something maybe in the high 90s or above 100 because of your rounding and because of your data acquisition techniques. Okay? So it should be close to 100. But in a perfect world, it would be exactly 100. All right. So realize that when you calculate a percentage of anything, like if I say I'm a 70% free throw shooter, what does that mean? That means on average, if I take 10 shots, I'm going to hit 7 of them. Okay? That doesn't mean I'm just going to walk up the line and shoot 10 shots and automatically hit 7. That means overall, on average, if I average all my trials together, that's about what I would shoot. So I would take the part. How do you calculate 70%? You take 7 divided by 10, right? Same principle applies. The part divided by the whole. You would take, like if you were doing percent composition of carvone of carbon, you would take however much mass of carbon you found present divided by the mass of the entire compound. The part divided by the whole, and you get a percentage. Move the decimal place over 2 places, you got your percentage. Okay? All right. Now, this slide is titled Mass Percent as a Conversion Factor, because we can use anything for a conversion factor as long as we can say that it's equivalent or equal. Okay, if I can come up with the mass percent of something, for example, if I know that sodium chloride, let's just say that I know this. You can determine this on your own in lab, but let's just say it's given. If you know that sodium chloride is 39% sodium by mass, okay, 39% of a sodium chloride's mass, a molecule's mass, is made up from sodium alone. Okay? What that means, what does percent mean? Anybody know what actually it means literally? Per and cent? Huh? Okay, what does per mean? Do you know? Of, actually literally when translated means of. So of 100. Okay? So 70% is 70 of 100, right? Because you got it by taking 70 divided by 100. that kind of thing. So since certainly means 100, so of 100. That means that you could assume a hypothetical situation. If you have if you know that sodium chloride is 39% sodium by mass, that means if you had 100 grams of sodium chloride, what would be the mass of the sodium present? 39 grams, right? That makes sense. If you have 39% by mass, that means 39 of 100. So that means if you just pick 100 grams as a hypothetical sample, if you had 100 grams of it, of sodium chloride, you would have 39 grams of sodium present in that sample. Okay, that's what this tells us. Guess what? That can be a conversion factor. We know that 39 grams of sodium are present for every 100 grams of sodium chloride. Okay? There you go. That's operating under the assumption that you are given a mass percent of an element in that compound. So there you go. Okay, that's how it was calculated. 39 grams over 100. So if I'm given, for example, if I say, all right, you have 17 grams of salt. You tell me how many grams of sodium are present in your 17 grams of salt. This is all you need to know. You need to know how much percent composition sodium is in sodium chloride. Because once you know that, you can say this. Okay, I have 17 grams of sodium chloride. What I know to be true is that for every 100 grams of sodium chloride, there would be 39 grams of sodium based upon its percent composition, right? As such, you can cancel things out. You're going to get an answer in grams of sodium here. Okay? Now, the key to all of this is getting to know and finding out this percent number right here. You're going to see that there's a whole separate procedure, just if that's not given to you, how you deduce it. It's a pretty good laboratory experiment. We'll actually run it. Okay, now likewise it would be true. Let's say that I needed to consume, for various reasons, I needed to put in my body today 20 grams of sodium. I needed 20 grams of sodium atoms because I figured up how many moles that would be, and that's what I need to sustain my chemical reactions that go on inside me. If I needed 20 grams of sodium, how much salt do I have to eat to get 20 grams of sodium? Okay? You would take 20 grams of sodium, that's what I want. Okay? 20 grams of sodium, how many grams of sodium chloride would I have to eat to get that much? Well, I know that for every 100 grams of sodium chloride, I can get within it 39 grams of sodium. So I position it where those things will cancel out, and I can figure out how many grams of salt I would have to eat to consume that much sodium. Okay? All right. Let's do a couple examples here. C2H5OH. Some of you may be quite familiar with this particular compound. I'm not judging anyone. I'm just saying some of you might be familiar with it. Anybody know what that is? Hairspray? Not quite. Although the people who consume this may quite at some point in the night consume hairspray. Who knows? This is ethanol. Ethyl alcohol. Okay? So hairspray is probably not out of the question at that point. I've heard crazier. So, all right. So there's the formula for ethanol. I want you to use that formula. Okay? Use this formula, and whatever it is that we've talked about so far, figure out the percent composition for each element in that formula. What percentage of ethanol is carbon? What percentage is hydrogen? What percentage is oxygen? Now we've got to use masses to do this. Okay, here's how we do it. Here's what we know. Okay, if we had 1 mole of this compound, then we know that there would be 2 moles of carbon present, right? There would be 6 actually. This is separated. Don't worry about why. That's farther down the road. Just realize there are a total of 6 hydrogens there. There would be 6 moles of hydrogen present if there was 1 mole of that, and there would be 1 mole of oxygen present. Okay, let's add up those masses. Keep them separate. Calculate them. 2 moles of carbon is this much. See how I got that? I looked it up on the table and multiplied it by 2. 6 moles of hydrogen would weigh this much, 6.048. 1 mole of oxygen would weigh 16 grams. Okay, guess what I do now? That's exactly right. I take the parts divided by the whole. So the whole would be all these things added together, right? The part would be each one individually. So I know that if I add this up, here's the answer I get right down here. 46.07. That's the whole. So let's look at carbon. Carbon, if you look back, it was 24.02. That's what we said how much was there. Okay, in 2 moles of carbon, it would be 24.02 grams. Okay, divide that by 46.07 and you get 52.14%. Easy enough. If you do, what's next? Hydrogen or oxygen? Hydrogen was 6.048 divided by the whole, the same whole as up here. You get 13.13% hydrogen. 16 grams was how much oxygen we would have in 1 mole of oxygen, divided by 46.07 grams for the whole. You would get 34.73. So you could see that most of the weight is due to carbon, then oxygen, then a lesser amount due to hydrogen. That's how you can come up with percent composition. That's assuming that you know what your chemical formula is. Okay? All right. So, percent composition of carvone, we're back to that. Okay? If a 30-gram sample contains 24 grams of carbon, 3.2 grams of oxygen, and the rest hydrogen, what would be the percent composition? Now, the last thing I asked you about carvone was, if I have this many grams of the actual compound, how many grams of carbon will be present? This is an extension of that same problem. Okay? We're going to look at all the elements involved as opposed to just carbon, and we're going to use the percent. We're going to calculate the percentage presence of each of those in this compound. So let's look. First of all, I'm going to need to know, do you see a problem with any of this data up here? Is there anything I'm missing? I don't have the formula, okay, but we'll worry about that in a second. Most importantly, I don't have a mass for hydrogen, but I can figure this out, right? How? Easier than that. That's right. I add these two together, and the difference between 30 and the addition of those two is how much has to be made up by hydrogen, right? Okay, so that means that's easy to solve in terms of just the mass of hydrogen that's present. No big deal. All right. So that's what I did in this step right here. That's how we did that. So we know, let's reword the problem. What is the percent composition of carvone, of all the elements involved within it, which are 3, carbon, hydrogen, oxygen? What is the percent composition of carvone if you have a 30-gram sample? Okay, now in a 30-gram sample, what we're saying is we have 24 grams of carbon, 3.2 grams of oxygen, 2.8 grams of hydrogen. This is easy, right? Only thing I have to do is divide the parts by the whole. That's what I'm doing here. It's going to be 80% carbon, 11% oxygen, 9.3% hydrogen. Okay? Got it? Got it. Good. I'm going to leave you with this. We're going to talk about this before we go. All right. Empirical formulas. Empirical is in reference to you deduce these from gathering data. This is where it gets fun, because this is where you can start taking unknown things, figuring out what they are. If you know everything that we've done so far, and up into that, if you can take an unknown sample, run some tests on it, and somehow figure out the formula, then you can answer all these questions that we just did. The key is determining the formula. And there's some neat ways that you can go about doing this. The easiest way is to use the instruments like you see on TV, like a GC mass spec or whatever, coupled with maybe NMR and some IR and all kinds of other stuff. But also realize that that would take several weeks to do, not a half an hour. Okay? It would take probably more than several weeks. It would take a long. I mean, I've spent a whole summer doing that kind of stuff before, only working with a couple compounds. So, all right. What the empirical formula is the simplest ratio of all the atoms involved in this formula. For example, the formula for glucose is C6H12O6. Now, that means literally in one glucose molecule there are 6 carbons, 12 hydrogens, and 6 oxygens all stuck together. However, is that the simplest way to reduce all of those terms? No. What's this? If you reduce all of those down to the simplest ratio, what would you have? CH2O, thus carbohydrate. I went over that already, didn't I? Explain why carbohydrates were called carbohydrates. Okay. All right, so CH2O, realize that when I say this, hear me. CH2O is the empirical formula for glucose. It is not the actual molecular formula. It is the empirical formula. It's the most reduced form of whatever its formula is. Okay? Now what you've got to realize is that when you run an analysis of something and you stick something in a machine and it's spitting back to you like, okay, you've got this proportion of carbon present and this proportion of hydrogen, realize that what that machine is actually going to tell you is just that. It's going to tell you you've got twice as much carbon as you do hydrogen, so your empirical formula is going to be C2H or whatever. That's not going to happen, but let's say it did. So C2H. That doesn't mean you know what that chemical is. You've got to do more tests because you need to know, is it C2H? Is it C4H2? Is it C8H3? The possibilities are endless. But what you do know is that the empirical formula in its most reduced form. Okay, that's what I'm talking about here. Okay. Realize that the molecular formula is going to be a multiple of the empirical formula, right? If you have the empirical formula of, let's say, C1H1, so CH. The molecular formula for CH is 13, right? 12 for carbon, 1 for hydrogen, 12 plus 1 is 13. What is the weight for the molecular formula of C2H2? What is that? How much would it weigh? 26, right? 2 carbons, 2 hydrogens. Guess what? 26 is a multiple of 13, right? 13 times 2 is 26. You add another 13, you can go up to 39. What you will see is that the actual molecular formula of anything is going to be some sort of factor, some sort of multiple of the actual empirical formula. So once you figure out what the empirical formula is, you're close. What you've got to figure out now is how many times do you have to multiply that to figure out what your compound actually is, right? Ignore that. That's incredibly too complicated. It takes something that's not hard to grasp and makes it harder than what it is. So don't worry about that. All right, we'll leave with that. We'll start with empirical formulas next time. Hopefully.